Hi folks, welcome to lesson 3 of vectors. So in the last lesson we saw how we were able to define operations with vectors, namely operations that looked a lot like what we did with numbers, addition and subtraction. So if we're going to consider addition and subtraction, at some point we might ask ourselves what happens when I subtract a vector from itself. All right, so let's take a look at our two views of subtraction. So one way of subtracting is to take a vector and instead of doing a subtraction is adding the opposite of the vector. Okay, so when we add vectors, we add them tip to tail. So let's take u and let's add vector negative u, the opposite of u, and let me place the tail of the second to the tip of the first. And what happens when we add, well, the resultant vector goes from the tail of the first to the tip of the second. And we see that the tail of the first and the tip to the second are in the exact same place. So essentially it's taken us back to where we started from. Okay, so we're going to have to find a way to describe a vector that seems to have no magnitude and no particular direction. Okay, let's try our second view of subtraction and make sure we get the same thing. So our second view is if we place the vectors tail to tail. And we said that the resultant vector of a subtraction is from the tip of the second to the tip of the first. But of course, the tip of the second and the tip of the first are at the exact same location. So we essentially have the same result, which is good because that's what we want. So we need to define a vector that represents something with zero magnitude, meaning there's no length, and really that has no direction because essentially you're not going in any particular direction. And not surprisingly, this is what we call the zero vector. All right, so it's very important here. Now instead of bolding it, I did use the arrow, okay, that the zero vector represents the vector with no magnitude or magnitude 0 and no defined direction. Okay, now we see that we need such a vector in order to deal with something like the subtraction of a vector from itself. All right, we're going to see later on how the zero vector is going to become very important for us. Okay, so if you look here at the definition, the zero vector, so make sure that when you're designating the zero vector as opposed to the number 0, that you put the little arrow on top, is defined as the vector with magnitude 0, no defined direction. All right. Now, when we're talking about operations like addition and subtraction, well, we might ask ourselves, are they commutative? Now, we already saw in the last lesson that vector addition is commutative. So u plus v turned out to be the same as v plus u. We also found, similar to numbers, that when we subtract vectors, well, they're not the same, but they are opposites of each other. In this case here, the vector u minus v is the opposite of the vector v minus u. And this is what we call being anti-commutative. All right, so not commutative, but still a relationship. Okay, now we just justified this idea that if I subtract a vector from itself, okay, we get the zero vector. Now this is not something we'll show, but I think it's fairly straightforward that if I take a vector and I add to it the zero vector, well, I'm adding, say I take my vector u, I'm adding something, say I go tip to tail, well, there's no magnitude and no direction, so essentially I stay exactly where I am. So I just get the vector u back. All right, so let's take a look at some of these other properties. Now, we're not going to confirm all of these. I will let you know that when we take an alternate view of vectors, we're going to have a way of proving these things much more easily. But for now, we just want to get a sense that these are true. So I'm going to take a look at this next property, which is called the associative property, okay, which tells you that if I'm adding a whole bunch of vectors, it doesn't matter which ones I add first. So whether I add u plus v first and then to that I add w, or first I add v and w and then add u, I should get the same resultant. All right, so let's take a look here. So let's add u plus v plus w tip to tail. So we just do that and we go from the tail of the first to the tip of the last, and there we go. There's our resultant vector. But of course, very often when we're adding vectors together, we might want to add them two at a time. So let's see what happens if I first add u plus v. Okay, so I get this vector here. Okay, and then to u plus v, I add the vector w. In other words, this addition, first adding u plus v and then w, and I see that I get the exact same result as I did before. Okay, and now let's do it in a different order. Okay, let's first add v plus w, get this vector here. Oops, there we go. Okay, and now I'm going to take vector u and add the vector v plus w. Well, lo and behold, I get the same resultant as before. So we see that whether I add u to the resultant of v plus w, or first I add u plus v and then to that I add w, I get the same answer. So that means that vectors are also associative under addition. Okay, so it doesn't matter which ones I add together first. And let's take a look at another one, what we say distributive under scalar multiplication. Again, a property that we would like vectors to have when we're using scalar multiplication. Let's just justify that we can distribute this scalar multiplication to a sum of two vectors. All right. So let's say I start with u plus v. All right. And let's start by adding those two together. So there's the vector u plus v. Then let's make it multiply that by 2. So we see here we have the vector 2 times u plus v. Is that the same as distributing the 2? So let's just justify that here. Okay, so let's take instead 2u plus 2v, and look what we get, the exact same resultant as before. So whether I do 2u plus 2v, or first I add u plus v and then multiply by 2, I get the exact same resultant. So this justifies the fact that it's distributive under scalar multiplication and addition. Okay, then there's another couple of others here that again we'll be able to prove more easily later on, and I don't think that's too surprising that if I'm multiplying by two scalars, it doesn't matter in what order I do it. I could multiply the scalars together first, then times the vector, okay? Or I could multiply one scalar to the vector, then multiply that other scalar to the resultant, same answer. And we see another type of distributivity, okay? So what that tells us is, say I've got 2v plus 3v, I can write that as, well, 2 plus 1. Sorry, I said 2v plus 3v. If I add together the coefficients, I get 5v. So in other words, we see that vectors behave algebraically a lot like numbers and variables. So essentially what these properties tell us is that we can treat vector addition, subtraction, and scalar multiplication like we would those operations with numbers and variables. All right, so let's do a couple of examples to show how we can now work with vectors as though we were working with numbers and variables. All right, so say I have this long, complex operations on a series of vectors here. Well, can I simplify this? Well, let's see what we can do. Well, first of all, we have the distributive property here. Okay, so here we have that we can write 2 times vector u. Okay, 2 times, well, remember what that other property told us. Okay, if we look here, when we've got two scalar multiples, doesn't matter what order we multiply. So this is just going to be minus 6 times vector v. Similarly here, this is going to be 8 times vector w. And now I can do the same thing here, do another distribution. So plus 12u minus 6w. And then here, this is just going to be plus u minus v, and then minus 2w. Okay. Now we can use the associative and commutative properties to change these around in whatever order I like. So in particular, I'll bring all the ones that are, I'm going to use the, like terms, because these do behave like terms. So I'll choose to write it as 2u, okay, plus 12u, okay, and then plus u, okay, and then I'll bring the v's together, minus 6v, all right, and then minus v, and then finally plus 8w, minus 6w, and then minus 2w. Okay, then that other property here that allows us to just essentially add or subtract like terms. Okay, so now we can do 2 plus 12 is 14 plus 1 is 15u. Okay, negative 6 minus 1 minus 7v. And then 8 minus 6 is 2 minus 2 is, well, 2w minus 2w. That's just going to give us the 0 vector. But of course, we don't need to write this 0 vector because we saw in this property here that adding the 0 vector to a vector has no effect. So we can write our final answer as 15u minus 7v. All right, and there's our final answer. So this complex grouping of vectors, instead of adding and multiplying them all individually, I could first simplify, and now that leaves me with a much easier operation to perform. All right, so let's take a look at another example here. Okay, so they tell us that vector u is defined as 4 times vector x minus 5 times vector y, and 3 times vector v is equal to negative 3 times vector x plus 4 times vector y. And what they want us to do is they want us to write x and y in terms of u and v. So just write in a different way. So again, remember, we have access to the same algebra now as we did with good old regular old algebra with numbers and variables. So what I'm going to do here is, well, I'm going to use good old elimination. Okay, so what I'm going to do is I'm going to consider this, say, equation 1 and this equation 2, and I know that I can use scalar multiplication, that whatever I do to one side of the equation, I do to the other side of the equation. So I'm going to rearrange these in order to be able to eliminate one variable at a time. All right, so let's start by eliminating vector x so that all I'm left with is vector y. Okay, so I'll take equation 1 and I'll multiply it by 3. Okay, so again, I'm multiplying 3 to this subtraction. I can use just the distributive property, so that gives me 12x minus 15y equals 3u. And then to equation 2, I'm going to multiply by 4. And so here I get negative 12x, 4 times 4 plus 16y equals 4 times 3, 12v. Okay, and now as I do in elimination, now I'm going to add these two together. Okay, so now I'll do, well, 12x plus negative 12x. Well, that's 12 times vector x minus 12 times vector x. That's just going to give me the 0 vector. Okay, negative 15y plus 16y is just going to give me vector y. And on the other side, 3 plus 12 is just going to give me, 3u plus 12v. And look what I now have. I now have y written in terms of u and v. Okay, and I can do something similar to eliminate vector y in order to write x in terms of the other two. Okay, so let's do that here. So if I want to eliminate the y's, I'll multiply by 4, multiply by 5. So 1 times 4 gives me 16x minus 20y equals 4u. All right. And then I'll do the same with equation 2, except now I'll multiply by 5. So we have negative 15x plus 20y equals 15v. All right. And again, I'm going to add these two vectors. So here I have 16x minus 15x is just going to give me vector x. Negative 20y plus 20y is again just the 0 vector. And then 4 plus 15 is 19v. And so here I can now write vector x. Oh, sorry, made a mistake there. These are two different vectors. 4u plus 15v. Sorry about that. So vector x can be written as 4u plus 15v. Okay, and this essentially is just an exercise to show that vectors can be operated on in a very similar way as we do with algebraic expressions that represent just numbers. All right, so just to recap here, we need to understand what the 0 vector is. Okay, we have all these properties that allow us to treat vectors and scalar multiplication as we would algebraic expressions when dealing with real numbers. All right, that's it for this lesson.